Hi guys, in this video we'll begin looking at alkene reactions. We have our outline here, written outline. We also have our sort of summary of reactions here, summary of electrophilic addition reactions to alkenes. And we'll proceed sort of here and work our way around with Roman numeral 1 first, and then we'll move to Roman numeral 2 and work our way around there. And each of those reactions are listed here on the outline. The first reaction we'll look at is addition of HX to give alkyl halides. This is also known as a hydrohalogenation reaction. It's shown here. X is typically referring to a halogen, and this includes like HCl, HBr, or HI. And as we said, we'll get an alkyl halide. Now this is just a representative alkene. It happens to be cyclic, but it doesn't have to be. We'll see lots of those particulars as we go along, and we do various examples. This is just sort of a summary. Okay, let's begin with addition of HX to alkenes to give alkyl halides. That is shown on the other handout, which I might call the board work. And if we look here, this alkene will react with HBr to give an alkyl bromide. And it is an addition reaction because this molecule now has the elements of HBr added to it. We can see that in the formula. This formula has HBr added to it to give the new formula for the new compound. Addition of HX is a common reaction of alkenes. Typically either HCl, HBr, or HI. Typically not HF, because F- tends to be a very poor nucleophile. Now I'm not going to explain every term the first time we use it, but we will need to more and more understand what we mean by nucleophile, electrophile, and other various terms. Okay, importantly for all reactions we do, we need to know and understand the mechanism. That is, how does this reaction take place? We cannot just rely on memorization, and we cannot just think maybe it's magic. We need to understand the underlying chemistry. Okay, why do these react? Well, HBr is polar. We can show it covalent as shown here. If we show it covalent, the H has a partial plus charge and the Br partial minus. Now we could also show the HBr as ionic. For example, if it's in a polar solvent, it's going to be ionized. So either way actually works. But dry anhydrous gaseous HBr is going to be covalent. Either way, we have an H that's either partial positive or full positive. Now the alkene has pi electrons, and the pi electrons are not held that tightly between the two nuclei. They're not held as tightly as sigma electrons. The pi electrons almost react as if they're a lone pair. Now if that was a lone pair, you know, like if we had a nitrogen with a lone pair or something, these electrons would attack the H, which is partial plus, and these electrons would move here. Standard acid-base that we did during test 1. But here it's the pi electrons that attack the H. Now, we have to decide where's the resulting H going to go? Now in this case, the resulting H ends up bonded to the carbon on the right. Here we didn't have to worry about that because the resulting H is bonded to the nitrogen. Okay? Because it's clearly this atom is making bond to H. But here, which carbon is making bond to H? Okay, what we need to look at here or consider, and this is typically the way it's presented, is these pi electrons are kind of connected to both carbons. They're going to hinge out like this. They stay connected to, here are your two carbons, okay, right here. I'm holding the two carbons. They break away from this carbon and they're going to hinge, and now this carbon over here is bonded to that H. This carbon is no longer bonded, is not bonding to the H. That's what this is. Take those electrons. Here's the double bond. Okay? I don't have like a ring or something. There's the two carbons with the electrons between them. Okay? Take those electrons and pull them away from this carbon, and hinge them up and go make bond to that H that's up there. So which carbon is now bonded to the H? Well, it's this one. And this carbon over here has lost electrons because this is no longer pi bonded over there. That's what that mechanism arrow means there, okay? Pull those electrons away from the left carbon, bond to the H, okay? I like to often illustrate what bond did we just make. Right there is the bond we just made as we pulled those electrons away and made bond to that H over there. That's the result here. Now the second arrow, what does it mean? That's just like the acid-base reaction. That's just like here. The bromine now has a fourth lone pair, and it is now minus. Well, that's the same thing here. We formed Br minus. But in terms of the organic intermediate, it is a carbocation, a carbon with a positive charge. There's your intermediate. All right, step one. Okay, step one is alkene reacts with H plus. Okay, now this is not mechanism, this is me explaining. Now you could call this addition of H plus, because we added an H. I don't particularly like that terminology because it sounds like we're throwing something at the alkene. No, the alkene is really attacking the H. But that is what you'll see is the terminology here. To give a carbocation intermediate, the H is on this carbon. We'll explain why below. So that's our first elementary step of the overall mechanism. The next step is the Br minus. These electrons make bond to the carbocation. Why would that happen? Well, negatives are going to be attracted to positives, and this is going to make a covalent bond, and there we go, we made that bond, and there's your product. It's a two-step mechanism. Keep in mind that the arrows show movement of electrons, not atoms. Okay? In this mechanism, the H plus is the electrophile. It's the thing that's electron deficient. The Br minus is the nucleophile. Okay? Nucleophiles are electron rich. We see that it's an anion. Nucleophiles attack electrophiles. The carbocation is also an electrophile. The H plus is the initial electrophile. Two-step mechanism. Again, if you wanted to show the HBr ionic, you could just do that. Either way works for me. We'll talk more about that. Reaction coordinate diagram. Well, from that video we learned how to do that. We're going to have reaction progress this way, and we're going to have some type of energy here. We start out with the alkene. We call that A. The organic intermediate we can call B, and the final product we can call C. A is somewhere arbitrarily here. We're not really labeling the axis, but let's say A. Our first intermediate, our only intermediate, the carbocation, is going to be higher in energy because it's charged. So we're going to show it higher in energy. And then the final product, C, is back to neutral. This is going to be back down similar to A, but will it be higher or lower than A? And actually, this is where you might pull out your calculator and do a thermodynamic calculation, but we should be able to qualitatively assess this, and we've gone from a pi bond to 2 new sigma bonds. CBr bond, but also the CH. Okay? You got to remember that there's an H added to the N carbon. The N carbon here has 2 H's. The N carbon here has 3 H's. Where did it come from? Well, the first step in the mechanism resulted in an H being added to the N carbon. I drew that H here just to indicate that we had added the H. I did not draw it here because this is drawn as a typical line bond structure with H's not shown. One of the common problems for beginning organic students is you lose track of where H's have been added or removed because we don't always show them. So we made a CBr bond and a CH bond, 2 sigma bonds, the pi bond's broken. This should be more stable. We made stronger bonds in place of the weaker pi bond. So this should be more stable than A. The reaction is overall exothermic. And if we draw the reaction progress, it's going to look like, there's your first step. And then from there, it's going to be, bam. And the first step should be the addition of the H plus, the alkene attacking the H plus. And that's going to be your overall activation energy. All right. And this is your rate determining step. If that's rate determining, we call this the fast step. What happened in the fast step? The nucleophile adds to the carbocation. I like always clarifying what's going on here. If you do that, it's a way to help you recognize what's going on here. The Br is a nucleophile adding to the carbocation. So that's fast. This is a rate determining step here. How do we know that's the rate determining step? Because it's the step with the highest activation energy. It's going to be the most difficult step. This step is easy because we're falling back downhill, and it doesn't take much activation energy, a little bit of activation energy, to fall back down to the level of C, the final product. What is this right here? We have a transition state here, and we have a transition state here. This is where that bond is being made to the H, and the bond is being broken between the H and the Br. That's actually sometimes called the activated complex. That's the highest energy part or point between in conducting the elementary step. And once it's fully formed and fully broken, then we fall into this sort of energy well, a discrete intermediate, and then the second elementary step can take place, but that is a fast step. Is this reaction thermodynamically favored? Yes. It's exothermic. As we showed here, I get a lot of students saying, yes, it's exothermic, as shown here. Well, we showed this. So just because we showed it, that's not the proof. The proof has to be more than we showed it, because we could have showed it wrong. We need to explain why it's exothermic and why we showed it this way. The reason it's exothermic is because product C is more stable. It's lower in energy than starting material A. Rate determining step, well, we identified that. Okay, that is a rather simple addition of HBr to this alkene. Note that the above reaction is regioselective. That is, we did not get this product. Okay, now we got the tertiary halide, not the primary halide. Why does the bromine end up on the tertiary carbon and not the other carbon? Okay. Unless you have a skeletal rearrangement, whenever you do an addition, you're going to be adding groups to the two carbons of the original alkene. But why did the Br end up on the left carbon and not the right carbon? Well, it all has to do with the carbocation intermediate and the stability. A tertiary carbocation is more stable than a secondary, and it's more stable than a primary, and it's more stable than just methyl, because a methyl carbocation is not even primary. Why? Well, it's inductive effects. All right. We'll look at this. What type of carbocation did we form in the reaction above? A tertiary carbocation. Okay, that is, this carbon is connected to three other carbons. And so these sp3 carbons all donate inductively to stabilize that carbocation. Yes, it's still a cation and still high in energy, but it's not as high as it could be if it was maybe secondary or primary. For example, if we did the reaction below and we swung the electrons the other way, that is, away from the carbon on the right, and the bond on the carbon on the left became bonded, opposite of what we did before. That is, if H plus was here, I'll show this as ionically. If the electrons swung away this way, Okay? And the pi electrons swung away from the carbon on the right and went up and bonded. And they went up and bonded like this, leaving the carbon on the right as a carbocation. That would be primary. And this carbocation only has one sort of rich friend. If I haven't used that terminology before, an sp3 carbon is electron rich. It can donate electron density towards the carbocation to help stabilize it, like a rich friend donating money to you. But guess what? The tertiary carbocation has 3 rich friends. All right, more stable. Now, if we call this carbocation, let's see, ABC, if we call this D, where would you put D up here compared to B? Well, it would be higher. And so let's put D up here. Now, it's the same starting material. So it would start out the same, but it's reacting, and instead it's going to form D, and so it would be reacting, and it would come up here like this. And so if you had a choice, which pathway would you take? Would you go and form B, or would you go and form D, the higher intermediate, higher energy intermediate? Well, you would form B. Water doesn't run uphill if it doesn't have to. Whenever it rains and water is running down the hill, if you ever see it come to a fork and there's an uphill or a downhill, I guarantee you it's going to go downhill. We'll come back and visit that analogy later. And so it's not going to proceed this way. Instead, it will proceed the way at the top. And so that's why, if it did proceed this way, we can envision the Br minus then attacking here, okay, these electrons, and that would give that product. But that does not happen. That is not the way the reaction proceeds. This reaction is regioselective. What does that mean? The bromine ends up on this carbon, not this carbon. Broaden that out, the bromine ends up on this region of the molecule, not this region of the molecule. These two at the top are called regioisomers. Okay? They're isomers. They have the same formula. In the context of the reaction, though, the bromine bonded to this region of the starting material or that region of the starting material. That's where that term sort of came from. Regioisomers are a type of constitutional isomers. We use the regio terminology when we're doing a reaction and talking about the outcome of the reaction, things bonding in certain regions. Okay, so we don't get this regioisomer. In the end, the outcome of the reaction is based on carbocation intermediate stability. You're going to want to form the best carbocation. And in this case, we ask, is it better to form carbocation on the left? That would be a tertiary carbocation. Or the right? That would be primary. And the answer is going to be always, unless there's some other exception we need to discuss, we would rather form a tertiary carbocation compared to a primary carbocation. Okay, Back to our outline so I can keep track and help you keep track. Did we cover the mechanism, including rate determining step? Yes. Did we do a reaction coordinate diagram? Yes. Discuss regioselectivity, carbocation, relative stability? Yes. Electrophile, nucleophile. Please work on understanding the definition of each. Ultimately, when we say pluses like minuses, that's like saying nucleophiles like electrophiles. Okay, on the second page of our handout, board work handout, predict the product of each reaction and tell if the reaction is regioselective or not. All right. I'll do the first one for you to take you through the thought process. What is the alkene reacting with? Well, ultimately it's reacting with the H, either covalently or ionically. Either way, HCl is a source of H+. And indeed, on the outline, the first reactions we're doing under A, they all involve a carbocation intermediate. Okay? And indeed we had one. There you go. And the electrophile is H+ or C+. Right now it's H+. All right. And if we just show this as HCl, that is H+. Because this is certainly partial plus, partial minus, and again you could just show that as H+, Cl- if you want. Alright, mechanistically these electrons attack the H. The question is, where do we want to make carbocation of the two original alkene carbons? Top carbon or bottom? And the answer is top, because it would be a tertiary carbocation. If we made it on the bottom, it would be secondary. So the pi electrons are going to swing up from the bottom. Okay? That is, here's your pi bond there, in that ring. We're going to swing up, hinge up from the bottom, and go attack that H+ that's up here, make sigma bond to it. Okay? Actually, no. That's not right. Because that would give the carbocation at the bottom. No. We want to come the other way. The electrons swing down from the top carbon, and we do this way. They hinge away from the top, come down here, and the bottom carbon is now bonded to an H, leaving the top carbon without any pi bond at all and no new sigma bond. Okay? There the top carbon has 4 bonds. When we move this one away from it, the top carbon now only has 3 bonds, and the lower carbon is bonded to the new H. That's what we're doing there with it. So when you do this, you want to grab up here and pull away from the top carbon. I see a lot of students draw the arrow from down here because they're like, well, this carbon is bonded to the H. Yeah, but how do you grab down here and pull electrons away from that carbon? You can't. Down here you would go this way. We want to pull electrons away from that carbon, and that's going to give, this is now bonded to an H, a new H, and we leave a carbocation at the top. Now, how many H's are on this bottom carbon? Well, there's 2 there, because there's 1 there to begin with. There's 2 here. I only drew in the new one. All right. Plus Cl minus, which came from that arrow there. Then the next step is these electrons add to the carbocation, and this gives our final product. And there we go. All right, I'm not going to draw in that H here, because I'm going to draw it as a standard line bond structure. There are now 2 H's on that carbon. One to begin with, but we added a new one. And so when you look at this, you got to see that the HCl is there that has been added. The Cl is clearly on that carbon, and there's a new H there. The Cl is there because that's where we would form the carbocation. We would never do this in reverse. Okay. Yes, it's regioselective. That is, I see that the reaction would not form the secondary carbocation and then Cl minus end up tacking at the bottom. It's not going to end up bonded to the other carbon. Not to that region. Okay, there are 2 for you to try on your own. Instead of HBr or HCl, now we have HI. There's no difference in your mechanism. Let's mention synthesis. Synthesis is where we're going to go backwards. And you will be asked to provide a reaction that would give these products. So how would you make this compound? Now, what reactions do you know? Well, the only reaction you know thus far, because we've only covered one, is reaction of an alkene with HX to give alkyl halides. Well, this is an alkyl halide, and you know that you can make it from an alkene. But the question is, which alkene? For example, would you want to make it from that alkene, or would you want to make it from that alkene? All right. Keep in mind, we want high yielding. We want the best synthesis. And the best would be to use this alkene, which, by the way, is what? 1, 2, 3, 4, 5. What is that? 1 pentene. And not 2 pentene. By the way, this is trans or E. All right. I would want to go back to this alkene. And note that I used a retrosynthetic arrow. I'm going backwards, one step back. I'm proposing, how would you make this product? I would go back and start with this alkene. It's my thought process arrow here. Now coming forward, I would react that alkene, I could show it like this, with HBr. And think about that, where we're going to form cation at, on the left or right carbon? And the answer would be on the left. And so this would form that carbocation. I'm not going to show full mechanism there. All right. And then the Br minus would then add there, and that would give product. All right. And I sense there's going to be some confusion about this. This arrow just shows how you would synthesize this reacting with H-bar to give that product. This is me just showing the second elementary step of the mechanism. Okay. So please don't think that we're going to go from here to here to here. Okay, I'm mixing two ideas here. This is going backwards. All right. The problem with this alkene is if you reacted with H+, where are you going to form cation at? All right. We could form either cation. We could form the cation there. Okay. Secondary, and let's call that A. You see, both of those are the same. But we could also do our mechanism the other way and get the cation there. And that's also secondary. So which is going to be favored? And the answer is neither. Neither are favored. They're both going to likely form. And when the Br minus attacks here, we're going to end up with this product here as a major side product. But we don't want that product. Okay, if you want this regioisomer, it would be best to start with this alkene, because this alkene reaction with HBr is going to be regioselective, where if you start here, you may get some of that product, but you're also going to get some of this product, and so that reaction is not going to be regioselective, at least not to the extent as this alkene would be. Okay, you can try the other ones on your own, including the synthesis of that alkyl chloride there. Okay, the next reaction we'll look at is addition of water to an alkene to give alcohols. And this reaction is a hydration of an alkene. And we can call it a simple hydration. And in this case, as shown here, we're going to have water, we're going to have H plus in water, and that's going to give an alcohol, because here, ultimately, the new group, the new nucleophile is going to be the OH group. And of course, that type of compound with the OH group, the hydroxyl group, is called an alcohol. All right. I'll let you also think about the regioselectivity below, which may be the favored product. But hydration of alkenes. First off, there's no reaction of an alkene with just pure water. All right? No reaction. The skin of an apple actually contains many alkenes, and those alkenes protect the inside of the apple from rain. And they do a good job at that. Now, if you start getting acid rain, we could start maybe having a problem, because the alkene will react with H+. We showed that over here. The alkene reacting with H+. Now, if we have H+ in water, which, by the way, if you combine those, we have H3O+, we can get a reaction. And if water is the nucleophile instead of a halide anion, you're going to end up with an OH instead of a halogen. And this shows a typical hydration reaction where we're adding water using acid catalyst. And if you look at the formula now has H2O added to it. So it's obviously an addition reaction. Now this reaction is also regioselective. We're going to get this alcohol, so-called tertiary alcohol, and not this primary alcohol. Mechanism. Well, it's just like before. The first step is the alkene. reacts with the H+. Now here I'm certainly going to show it ionic, because here I'm using sulfuric acid as the catalyst. Typical catalysts are sulfuric acid, phosphoric acid, or HF. Alright? Now the first two are typically always aqueous, and if it's aqueous it's going to be ionized, and we can certainly show H+. Now the alkene attacks the H+. The question is, where are you going to leave cation, on the left or right? Well, the answer is on the left, and we're going to make a tertiary carbocation. Same question we would have asked and answered before. The next step is some type of nucleophile adds to the carbocation, but the only nucleophile around is water, and these electrons add to the carbocation, and now the oxygen is bonded to the carbon. Alright. Now note, these two H's are still there. We don't magically lose the H's. We need a full Lewis structure here. Now, the next step, and we need a full Lewis structure here as well. This is the conjugate base here, and this is O. Okay. And here we have a final step where these electrons take the H. Let's just get rid of that. And then these electrons move on to oxygen to become second lone pair. And now the O has taken the H, and H2SO4 has been reformed. You can just show it like that, but of course if we show it out, that oxygen now is bonded to the H. That is this. And so the catalyst has been reformed. Definition of a catalyst. Now, you could instead use water to take the H. Because this is an aqueous acid, okay? Water is here. If we use water, these electrons take the H. We would form, instead of H2SO4 forming, we would form H3O+. That's actually more correct. Because, how does sulfuric acid exist in water? Well, it exists as H3O+ and HSO4-. So if you form that, you're actually and strictly more correct. I, though, actually like to use the conjugate base of the acid, so I reform the actual catalyst. Because I like to reinforce to you that, look how we reformed the catalyst. It was used, but it was reformed. Yes, in both instances, this is really H3O+ and bisulfate anion. But if that's all you knew, and someone said, hey, it's sulfuric acid catalyst, you would not know how to deal with it. All right? Either works. If you want to use water, that's fine. I will always use the conjugate base. Something needs to take the H. We don't just magically lose H's, and that's where the the second lone pair comes from here, and we understand the idea of a catalyst being reformed. How many intermediates in this reaction? 1, 2, let's see, 1, 2. 2 intermediates. We have the carbocation, And then we have the protonated sort of oxygen. It's really a protonated alcohol. All right. This is 3 steps. The first step is going to be the rate determining step. Forming the carbocation is typically the rate determining step in most all of these reactions. Then we start going downhill from there. Now, importantly, there's no other nucleophile here other than water. Now, there's certainly no halide because we didn't use like HBr. The bisulfate anion will never act as a nucleophile and add to the carbocation, not in this class. Neither will the phosphate anion, and neither will F-. Remember how I said earlier, F- doesn't work here because F is a poor nucleophile. All right. ClBrI-, these will add to the carbocation and give you an alkyl halide product. So if you want an alcohol, you should not have any ClBr or I- around. That's why you don't want to use HBr as a catalyst if you want to make an alcohol. You'll get an alkyl bromide instead. These are your best catalysts for hydration of an alkene. One last comment here. The first step of your mechanism is essentially a reaction of the alkene with the H+ catalyst, because the H+ comes from the catalyst. Because an alkene does not react with pure water, but it will react with the acid catalyst. Then water will come in here and do something, and we reform the catalyst. Now, I'll make a comment here. The hydration of an alkene is actually very reversible. If you take an alcohol, we can treat it with an acid catalyst and we can go back to the alkene, and that would be called a dehydration of an alcohol. And the mechanism is the exact reverse. That is, the first step going backwards is you protonate the oxygen to give this species, okay? We can come exactly backwards. And then from here, this protonated oxygen can leave the carbon, and that would give a carbocation. And then from here, something can take the H, and these electrons can move in, and we can remake the pi bond. Don't worry about going backwards right now. It's worth looking at. But we will certainly go backwards during test 3. And so I'm kind of letting you just know that right now. And really each step is an equilibrium. Okay, down below we can predict the products. We have an alkene, we have water and acid. Okay. H3O+, well, that's the same thing we had here, right? All right. Isn't that H3O+? You got to know that aqueous acid is going to be shown different ways. Aqueous acid is H3O+. Well, that's what we're shown here. And so we need to know what type of product this is going to be. This looks like a hydration of an alkene. There's also one here. This is acid. Looks like an H+ catalyst, yeah? HF. But it's ethanol. I don't see any water here. We're using a dry acid and ethanol. What could be the product here? think about that. We also need to think of stereochemistry with each of these products. Okay? Now, we haven't looked at any stereochemistry yet, but this will be sort of a first glance at it. And so we'll be kind of setting the stage for stereochemistry, but let's do that now because these examples are going to have good stereochemistry for us to consider. Or actually, when we learn about stereochemistry, we'll learn that this product here really didn't have any stereochemistry to consider. Okay. I'm going to sort of stop this video here. We'll move to carbocation rearrangements on the next video. But what I do want to look at is go back to remind you of this handout here. 2 mechanisms for making nucleophile to carbon bonds. And we did that during this video. Right here, the bromide made bond to the carbon. And it attacked a carbocation. That's an example of what I'm showing right here. Okay? Something with a lone pair that it may be minus charge. Typically it's going to have a lone pair, although it doesn't have to. It's the thing that sort of has the electron density. And electrons like positive charges, and the nucleus is typically positive. You know, if we call this a positive file, it might make more sense, but instead we call it a nucleophile because the nucleus is typically positive. Nucleophiles like positive things, either formal positive or partial positive. All right, but this also tells you the stereochemistry, which is important. All right. Because a carbocation is sp2 trigonoplanar. All right. Now it's that carbon is planar. All right, like that. Let's draw. It's flat. I can either put it flat on the table, or I can hold it like this. All right, if it's like this, like a piece of paper. And because of that, the nucleophile attacks either one side, okay, I'll turn this so you can see the plus. It either attacks here or it attacks here. 2 sides of the plane. And the nucleophile can attack from either side randomly. Thus it's going to be 50-50. If it's like this, the nucleophile can attack from the top, and thus it'll be bonded from the top. Well, let's do this. If it attacks from the right, bam, it'll just attack. It's going to be stuck like you threw a dart at it, and it's going to be bonded to the right. But if it attacked from the other side, which is just as likely, bam, it came in here and the nucleophile made bond to carbon. It's going to be to the left, just like a dart being positioned to the left after it came in and hit the dartboard. And so you're going to have some nucleophiles to the left or some to the right. Or if we had this like this, you have some straight up because it attacked straight up plane, but you can also attack from the bottom, okay, or the back. Here we go, or like that. If you came in from the back, the new bond would be back. If you came in from the front, the new bond would be front. And so that's how we can get the nucleophile being either front or back. It's going to be a 50-50 ratio approximately. All right. Please read this. I feel like I don't need to read the rest of that to you. You should look at it as if I just read it to you. All right. It's hugely important. So that's one way that when nucleophile, we can make nucleophile carbon bonds. The other way is for the nucleophile to come in and attack a carbon and kick something off. See, up here we didn't kick anything off. We just bonded to a carbocation. That carbon needed another bond. It needed a fourth bond. Here, this is like a replacement type reaction or displacement. The nucleophile comes in and kicks that off, and that's going to be called a leaving group. And now we have the nucleophile to carbon bond. But there's also stereochemistry involved with this type of reaction. First thing to know is that the nucleophile always comes in opposite side to where the leaving group is. So if the leaving group is forward, the nucleophile is going to come in from the back and thus be bonded to the back. If the leaving group is back, the nucleophile will come in from the front. Okay, it's always opposite. When you attack a carbocation, it's 50-50. Either top or bottom, or right or back or front. Okay? Carbocation is either 50-50. Whenever you kick off a leaving group or displace a leaving group, it's always what we call backside. Now, it might make more sense if you called it opposite side. All right? Because if the leaving group is back, the nucleophile comes in actually front side. The back side is reference to the position of the leaving group. Okay? It's always sort of opposite to the leaving group, or backside compared to the leaving group. These two are straightforward. This one down here is often either forgotten about or gives students a little bit more trouble. But here the leaving group is straight up. And so the nucleophile is going to come in straight down. Now that seems straightforward. Once we actually start doing this, you'll need to go back and revisit this, and you'll have a little difficulty with that concept there. Mainly because books tend to do more of these two and don't show you this as much. Now this will be important some during test 2, but will become even more important when we get to test 3 material. I like to present it now so you start thinking about these general ideas, which will be important for the remainder of the course. Okay? And so the stereochemistry we saw here will be important when you address the stereochemistry of these products here. All right? Okay. Let me end this video by showing a mechanism here in the warm-up. Very basic, but the thought process is what's important. We have K plus and Br minus. Of course, KBr is ionic. We can show that. What's happening here? The chlorine on the carbon in carbon is being replaced by the bromine. All right. And then we're going to end up with K plus and Cl minus. Now potassium is just a spectator ion. So ultimately Br minus is doing something and replacing the Cl, and it gets it comes off as Cl minus. Now, can we show a mechanism for this? Now, there's actually perhaps a couple of ways to do this, but the information is there is no intermediate in this reaction mechanism. So how can we get an all-in-one step, the Br bonded to the carbon and the Cl like this? Well, forming this is like the Cl minus, or like these electrons moving on to chlorine, like in an acid-base reaction. Wouldn't that give this? Yes. But we also have to form a carbon-bromine, and these electrons, okay, what did we just show over here? All right, nucleophile kicking off something. What about these electrons coming in here, making bond to carbon, kicking off the Cl? That bonding pair would move on to the Cl as a 4th lone pair. That would become minus, and the Br is now bonded to the carbon. And that's one step. There's kind of two concerted steps, but that's all one step. There's no intermediate. Okay? That's what we said. There's no intermediate anywhere. Why would the Br minus attack that carbon? Well, that carbon is partial plus. There's a dipole here, partial plus, and the Cl is partial minus. And so the negative charge is attracted to the partial positive carbon. And we can get a reaction. It's called a substitution reaction. So, some of the thought process that's there. Try this one below on your own. It's much more sort of involved, but it's also still straightforward. What bonds are you trying to form? What bonds are being broken? And just move electrons as you need. Now also, please keep in mind that you need to really read the guidelines on proposing and showing correct reaction mechanisms. All right. Very basic but very important information that I've organized here for you. Okay. Okay guys, we'll leave it there with our first video of alkene reactions, and we'll pick up next time with sort of in here 3, or specifically carbocation rearrangements and ring forming reactions. We'll do that on the next video.